Alright, so question number 12 was pretty cool, but it was there was something tricky about it. So, okay. So, okay, again, they want us to propose a structure. They give us a formula. C4H8O3, right? And then they give us a hydrogen, protein, NMR data. So they give us the chemical shift in parts per million. They give us the splitting. And they give us the integration, which is the number of hydrogens in each signal. So at 1.27, the most upfield, furthest away from the oxygens and the electronegative oxygens, there is a triplet signal, and it's 3 hydrogens high. Then at 3.66 chemical shift, there is a quadruplet, and it's 2 hydrogens high. At 4.13 chemical shift, there's a singlet, and it's 2 hydrogens high. And then at 10.95, there's a singlet, and it's 1 hydrogen high. So, and then they also gave us IR data. So they said there was a 2,500 to 3,500 negative reciprocal centimeters broad band. So that could be a carboxylic acid, maybe an alcohol. And then there was also at 1,715 reciprocal centimeters, there was a strong signal, and that's a carboxylic acid or a ketone, maybe. And I got all this information about the IR on page 86, table 2.7 in the Fryle and Solomon's book. So it was, I went and I said, okay, there's probably, from what I saw, both of these IR data gave me carboxylic acid. So I ventured and I said, okay, let's just put that down as a very strong possibility that there's a carboxylic acid. Then I looked and I said, okay, there are 3 H's that are far away from the oxygens. They're far away from the oxygens, and they are next to 2 hydrogens, 2 heterotopic hydrogens. So I said, I obviously have something that looks like this in my molecule. Then I looked and I said, there's 2 hydrogens, right, that are a little bit closer to the oxygen because they have a greater chemical shift. They're more downfield. And it's a quadruplet, so it's next to 3 heterotopic hydrogens, and that's just simply this CH2 next to this CH3 being split by these 3 into a quadruplet. Okay, and then there's a 2H. There's a 2H that's even closer. That's very close to the to an electronegative oxygen, and it's a singlet, so it's not near any hydrogens. So I wrote, okay, there's a CH2 that's not near anything attached to any hydrogens. There's a CH2 somewhere that looks like this, and then there's 1 hydrogen that's all the way downfield next to oxygens, and it's a singlet, it's not near anything, that would be the hydrogen attached to my carboxylic acid. So when I was trying to figure it out, this signal to me, I didn't find anything in the IR data that suggested that this was an ether, but I said the molecule was CH3, CH2O, CH2, COOH. I was looking, there's 3 O's, right? There's 3 O's, so the 2 O's are taken up by this carboxylic acid right here. So the other O either had to be a ketone or a was it like a ketone or an ether? And the ketone wouldn't necessarily isolate a CH2 like it does right here. It isolates the CH2. It's not near any other hydrogen, so it's not being split, right? The CH2 that's not being split, and it's near an electronegative atom. And then it just all makes sense. Here's the CH3 that's furthest away from everything, being split by a triplet by these 2 hydrogens right here. This hydrogen, these are the 2 CH2s that are closer to the oxygen because they're downfield, they have a greater chemical shift. This CH2, which is very close, it's in between, this oxygen and this oxygen, it's further downfield, it's closer to electronegative atoms. The singlet, it's not near any hydrogens, heterotopic hydrogens. And then, of course, here's the singlet, single H by itself over here. So even though an ether wasn't really expressed by the IR data over here, you just had to kind of think your way through it and find it. So now I'm going to go eat some vegan gluten-free pizza that my husband made for me because he's the best.